So we're now going to talk about the LockManager application case study. And this is going to show how we can use Spring WebMVC to send and receive HTTP GET and POST requests synchronously to and from a microservice that's going to provide essentially a distributed semaphore functionality. So if you're familiar with semaphores, semaphores are a form of synchronizer where you can have a count of the number of resources available, and clients can come along and acquire or try to acquire a semaphore. And if the count is greater than 0, then the client can get back a token or a permit, as it's sometimes called, and they can do their thing, knowing that that resource is theirs for that time. And when they're done, they give the resource back to the LockManager, the semaphore manager, and some other thread can come along. And it's typically used to coordinate interaction between multiple threads. And the way this is going to work is it's going to have synchronous HTTP GET and POST requests and responses. So let's go ahead and talk about this case study. And you can find this case study as usual in my GitHub repository, in the EX5 project, in the WebMVC folder, in my live lessons repo. So the client is going to make requests to synchronously acquire and release locks, either one at a time, like give me the next one, or I would like some of them, some N of them. So you can have multiple permits. And you can see here, this is what the interface looks like. This is actually an interface that we write that works with something called HTTP interface, which is a declarative mechanism for defining interfaces or proxies without you having to write any code. It's very, very cool. So we have this thing called the lock API, and we've got methods that we can use to create a semaphore, release it, acquire multiple things, release multiple things, and then release a given lock. So those are the methods. You can see if you take a careful look here, these are all just classic Java reference types or lists of reference types, and they're all synchronous. Nothing too surprising here. This is the same sort of thing you could have done with retrofit, but this is a cleaner way of doing it. The server, on the other hand, which is a microservice, of course, can also be used to acquire and release locks individually or in bulk. And it's got a controller that takes the HTTP requests, both GET and PUT requests, and turns them into Java types, and then forwards them to the LockManager service. And this is what the controller interface looks like. So it's very similar to the client side. That's this piece here. But there's a couple of interesting differences. The most interesting difference here is that acquire returns something called a deferred result. And a deferred result is a clever Spring mechanism that allows synchronous servers to be able to move the computation off of the incoming servlet thread. So you can have more processing without chewing up servlet threads. And we'll see how that works when we get to look at the code. Then we have the service, which internally uses an array blocking queue and virtual threads to implement a distributed semaphore. So this is very clever, and we'll talk about why we do this when we get a little further along. So this is the LockManager service interface. You can see we have an executor that's going to make these virtual threads. We have this blocking queue. We'll talk more about that keeps track of the number of locks or semaphores that are available. And then we've got all these methods. And these methods are very similar to the methods over here. Just they're the implementation methods, whereas these are the ones that form the interface between the HTTP world and the Java world. So just a real quick synopsis of what's in the project, client and server part. We've got the server, which does all the interesting stuff, and then we have a test client using the classic Spring Boot test mechanisms. The server has all the things you'd expect, like the application, microservice, the controller, and the service implementation. This uses good old Java conventional Java types. We have a common thing that defines some stuff that's shared between the client and the server, like the lock, for example. And then we have some utilities for logging. And then the resources define the port number and name of the service. The client side, the test side, has a test that initiates all the calls, that drives the microservice to make sure it's working. And it's also got this cool lock API thing that uses the declarative HTTP interface features that were provided in Java in Spring 6. And we'll see how that works. I think, like I said, it's much cleaner than using retrofit. And you can turn logging on and off. So what are some of the pros and cons of doing things this way? So the use of deferred request, we're going to talk about here in a second, helps to avoid blocking the servlet thread. And therefore, you can scale things up more effectively because you don't have to steal or borrow the thread of the servlet thread pool for the entirety of the computation. So that's a small benefit. We use a very clever use of array blocking queue to avoid having to know anything about synchronizers. So I teach another class here, which I haven't taught this year. I'll probably teach it over the summer, may teach it next year. And it is a class that's on concurrent object-oriented programming. And in that class, we have basically a whimsical example that riffs off of Lord of the Rings concepts and so on. It's called a Palantiri manager. If you know Lord of the Rings, you have Palantiri. So we can give them out to beings who want to gaze. And one of the goals of that class is to teach all kinds of cool synchronization approaches. But the initial implementation, I just wanted to give something that would work without requiring people to know anything about synchronizers, because we haven't taught it yet. So we use something called an array blocking queue, which is a bounded buffer mechanism that Java supports. And you can use it to implement this semaphore mechanism without having to know anything about how synchronization works, which is kind of fun. And then the client uses this declarative Spring 6 HTTP interface synchronous proxies, which simplify a lot of the coding on the client side. So those are good things. The downside is the client isn't actually asynchronous, only the server is, so we don't get end-to-end asynchrony. And there's also some issues where if client threads block for a long period of time, stuff can time out. I'm still figuring out how to make that stop being a problem, but that's the way it works by default. And the server uses the Spring WebMVC thread pool model, which doesn't take full advantage of Java virtual threads unless you know what you're doing and you're using modern versions of Java. And then finally, the array blocking queue implementation, however clever it may be, is not the most optimal way of doing things. There's much more efficient ways of implementing semaphores, but that's really outside the scope of what we care about in this discussion, so we're not going to dwell on that for now. We're going to address a couple of these limitations by using WebFlux and Java virtual threads. So after we're done with this set of discussions of Spring WebMVC, we're going to revisit the example, redo the whole thing with WebFlux, and then you'll have a nice Rosetta Stone to compare and contrast the two approaches, providing essentially the same functionality with very different concurrency and synchrony models. Okay, so that's the end of the overview of what this case study is all about.